So in this demonstration, we're going to focus on a specialized type of spatial modeling. That's hydrological modeling. So this is essentially how surface water is going to run across a particular topographic surface. So if you remember from the lecture that accompanies this demonstration, there's a basic order to how we do these hydrological models. Now essentially we're dividing this up into two big sections, both creating a stream network, so analyzing how water would flow across the entire surface, things like flow direction, accumulation, ordering and creating stream features, and measuring flow at particular points. So either looking at the stream networks to analyze how things are going to flow across a key location, or creating what we call pour points and then analyzing how much of an area is going to flow out through that particular spot. So essentially the watershed that contributes to it. So the basic order of these is we're going to start with looking for sinks in an image, in a DEM, so areas where water is going to flow into but not back out. Then we'll fill them. We'll work with the flow direction and then the flow accumulation. We'll turn this into a stream raster by doing a threshold. We'll calculate an order of the streams that are in it. We'll create a feature layer out of this, and then we'll work with different pour points to calculate watersheds for the area. So let's go ahead and get started. You should have in the demo data folder essentially just one layer. This is the same SRTM image that's in the previous demonstration and the topography demonstration. So feel free to reuse it if you don't want to download it. There's also one other file in here that's part of an optional assignment that goes along with this. This is for each soil class in St. Joseph County, what we call the E-risk or the erosion risk for it. So you can play around with that if you want to do the optional assignment. But once you've gone ahead and downloaded all of your data, switch back over to ArcGIS, and you're simply going to add in that one layer. If you need to have a refresher on how to map to a particular folder, I encourage you to look back at one of the previous demonstrations. But I'm just going to go straight into my GIS folder here, Demo 12, and add in SRTM, so Shuttle Radio Topography Mission, Michiana. This is a DEM, or Digital Elevation Model of this region. Go ahead and hit Add. You may or may not already have your Arc Toolbox up. If you do, you're ready to go. If not, you want to start it off by hitting the Arc Toolbox button up here. So we have a DEM here, taken from a satellite, or taken from a shuttle mission actually. And what we want to do is do all of these hydrological tools on it. And the base data for most hydrology in a GIS context for surface hydrology is a digital elevation model. You can start with a TIN and then convert it into a DEM, but you really need that grid-based system to accurately do a lot of these measurements. So the first thing we want to do is we're going to go into our Spatial Analyst tools. And almost everything we deal with in this demonstration is going to be in Spatial Analyst. And then almost all the tools we're going to work with are in the Hydrology section of the Spatial Analyst tools. The very first thing we want to do is let's just assess whether or not we have a good DEM to serve as a base map, or as a base layer. So we're going to start off by creating a flow direction here. So go ahead and click on flow direction. It's going to ask you for your surface raster. That'll be that SRTM. And it's just going to only then ask you for the output flow direction. All it needs to calculate this is the surface, the input surface. So let's go ahead and give this something permanent. I'm going to put it in my Demo 12 folder. And I'm going to call it Michiana Flow Direction Raw. Now why raw? This is a little bit of a spoiler, but we're going to work with one that we've done a fill on afterwards. So this is just to differentiate it from the flow direction that we're going to run a little bit later. Make sure you hit the .tif on there or it'll give you an error because the file name's too long for the type of system that it defaults to. So choose your TIFF, hit save, and go ahead and run it. So when this comes up, it's going to be coded for us in sort of an 8-bit way, so powers of 2, that shows us what the direction is. So a 1 is going to be straight to the east, a 2 is going to be to the southeast, a 4 is going to be to the south, and 8 will be to the southwest, 16 is going to be to the west, 32 is the northwest, 64 is north, and 128 is northeast. I don't expect you to remember those because they're in the slides and they're actually in the demonstration notes as well. So if you remember from the lecture, one of the things that we talked about with these images is that if it can't figure it out, if there's a pour point, or I'm sorry, if there's a sink in the image, if water flows into one spot, or if it's ambiguous about how it would flow back out, it's going to give it the sum of all of the different values that it could possibly be. So that's why we end up with things like 255. So we're scaled from 1 to 255. Most of the values in here are probably going to be 1, 2, 4, 8, 16, 32, 64, 128. But in any case, it doesn't know what to do. It's going to put them in there. So if you have values other than those sort of set 8 values that give you directions, what you want to do is run the sync tool to see where those areas are that are a little bit ambiguous. So let's go ahead and run sync now. So the sync is just going to ask us for the flow direction raster. So go ahead and drag that over. And I'm going to call it Michiana Sinks. .tif. So when you run this, it's going to look at that flow direction raster, and it's going to find all of the ambiguous areas and flag them a little bit differently for us. So it'll come up, and you can see that there's actually almost 12,000 spots in here that have some ambiguity. You can only really see this if we start turning off the other layers. And what you see is in some cases, these are lakes. This is the lake in Potato Creek State Park. Some of these other ones are actual lakes in the image. However, a lot of the other ones are just spots where that particular pixel was coded slightly below elevation-wise the ones around it. Or where two are essentially exactly the same and we don't know how water would flow across them. We have some peaks probably in there as well. So what we want to do to process something like this is we want to fill them, even in cases where we know that water actually flows in and maybe doesn't flow out for a while. It eventually does flow back out, or would if enough water got into it. So it's a valuable thing for us to be able to understand how the hydrological flow across the entire surface is, whether or not it's truly accurate, and whether water would whether there would be a reservoir of water there or not. So the next thing we want to do is run the fill tool so that we can get a sinkless DEM, a sinkless topographic surface to then use for all of the further analysis. So we're going to run fill next. In this case, it's going to ask us for the input surface raster. Always be very careful that you're looking for what it's asking for in there. In some cases, tools that you might expect could work off of the DEM will actually want the flow direction, and vice versa. So in this case, it wants the surface raster, so bring that in. And I'm going to call it Michiana DEM filled. So I'm going to change the name just a little bit and hopefully be able to spell. .tif. So now when I hit OK, it's going to run for a moment. And when it comes back up, we're going to have something that looks pretty similar to the DEM that we had in originally. So I'm just going to turn off all the other layers, but that original DEM, you'll notice that the values are slightly different. Some of the very low pixels have been raised up a little bit. And I'm going to change the color ramps just by clicking on the color ramp there. To be that standard elevation one, just so we can see the differences between them a little bit more clearly. So I can go ahead and turn one off, turn one back on, and you can see some of what's happened in there. So areas that were previously, I'm just going to zoom in a little bit on one here, areas that were previously very low but surrounded by higher topography have been filled up to a level where the water is going to flow back out of them. So it's assuming that there's quite a bit of water to give us a model of the entire surface here. So from here on out, this is the one we want to be working with. We're going to rerun a lot of these tools with this filled-in DEM that's going to give us a complete hydrologic model. So I'm going to turn everything else off. If you wanted to, you could remove them just so they're not confusing, as long as you've saved them permanently for any sort of assessment. So since we've run the fill tool, the next thing we want to do is rerun flow direction to give ourselves an accurate measurement of it. So go ahead and choose flow direction. And we're going to use this with the fill DEM. Ignore the drop raster, ignore all the other things in there. And I'm going to call it Michiana flow direction filled. So just choose the old one and just change what's in there. .tif. So I'm going to zoom back out to the full image so we can see this. And when it's finished running, what we'll end up with is something where there is no more ambiguity in there. So in contrast to the previous flow direction where we had anything from 1 to 255 in there, in this case we only have those actual directions. So 1, 2, 4 are powers of 2 from sort of east all the way back around, coded for direction. So we have an accurate measure of how water is going to flow across any given area on there. Now, if you remember from the lecture, from the way that we did this before, the way that we did it in sort of the demonstration lecture part, the next thing to do is flow accumulation. So we want to see how much water is going to build up in particular places as it flows across the surface. So we're going to choose the flow accumulation tool here and run that. In this case, it wants our flow direction raster. Just make sure you're giving it flow direction filled. And we're not going to worry about the rest of the things other than setting the output to be Michiana flow accumulation. So I'm just choosing old ones, so I have to minimize my typing since apparently I can't spell or type anything today. I'm going to call it flowac.tif. And hit OK. So what it's going to give us is a measurement of how much water or how many pixels are going to collect in particular spots. So we go from things where that pixel, nothing else flows into it, so zeros, all the way up to some spot probably on the edge of the image where 350,000, almost 360,000 other pixels flow through that one place. So that's an area where there's likely to be a lot of different flow there. So if we want to see it a little bit more clearly, we can go into the layer properties for it, over to symbology. And it's gone ahead and put a stretch on it, just like any raster image that comes into ArcGIS. Let's go ahead and just change it a little bit so we end up with a standard deviation stretch of 0.25. This will make everything a lot clearer in there, so we can sort of see the network of things that it's starting to put in. So what we want to do to go any further with this is we want to create what we call a stream raster. And to do a stream raster, this is one where there's not a tool over here for it. We want to threshold this image. So we want to say, okay, we're not worried about those places where only 50 other pixels flow into them. We're really worried about the bigger ones. Those are what's interesting to us. So that's what we actually want to measure. And this will make it so that there's a lot less data for the computer to process. It'll make things work faster and give us a better view of the actually important hydrologic channels and water flow channels across this area. So there's two different ways that we can do this, one of which we've already worked with before, and that's using the reclassify tool. And the other is using what we call a con tool. And this will go through and basically if it's one value, it'll give it one thing. If it's the other value, it'll give it something else. It's conditional is what it stands for. So either one is equivalent. I'm going to show you how to do both of them. Don't feel like you need to do both if one works okay for you. So the first part, just doing a reclassification here. In reclass, Spatial Analyst Tools reclassify. We're going to bring over flow accumulation. The reclass field is value. Choose classify. We're going to give it two different classes. And the break value in there is going to be 50. So this will be less than 50 pixels, one thing happens. More than 50 pixels, another thing happens. What we want this to be is actually if it's 0 to 50, we want to give this no data. We want to make this so it gets just tossed straight out of there. So, or just choose N, lowercase o, no space, capital D, A, T, A, just like the one that's down here. And if we want it in the other class, we're going to give it a 1. Let's go ahead and give it a permanent output. We're going to call it Michiana stream raster 01.tif. 01 is only because I'm going to do it twice. You don't probably need that. Hit save and OK. Before I go any further, just in case you start getting weird ghost values, just like we did in the past, remember that when it calculates these values that it's going to look at, it's maybe not looking at every single pixel in the image. It's taking 50, 25% of them and assuming that it's gotten whatever the variability is. If you end up with weird high ghost values still in there, you can always go into classify here and just change this maximum value to be a little bit bigger. So maybe instead of 35 over here, I'll just change it to be 37. So that's not actually changing anything that's in the image. It's not even changing anything that's in the classification, though it did sort of take away my pre-built values here that I just have to re-enter no data and 1. But what it is going to do is it'll catch any sort of ghost additional values that are in there. So go ahead and hit OK. Should run for just a moment. Going through, looking at every pixel. If it's less than 50, it gets no data. If it's greater than 50, it gets 1, and it'll create just those stream channels for us. It's not going to look like much happens until I turn off everything else, and you can sort of see that it's just thrown out all the values and given anything greater than that a 1. Now we do this so that we can then rank the values that are in there based on how many channels are sort of flowing together. So the other way that we could do this, just to step back for a second, the other way we could calculate a stream raster is to use that con tool that I was talking about. This is perhaps a little bit faster. We could either use the conditional tool that's up in here, or we can also simply do it in the raster calculator. So I'm just going to do it right in the raster calculator real quick. So you bring in your image, you load up the raster calculator, and all you want to do is hit con over here, Michiana flow accumulation. Before this, the comma there, you want to do is greater than 50. After the comma, give it a 0. So it's basically saying if it's greater than 50, or sorry, give it a 1. If it's greater than 50, make that value 1. If anything else, just ignore it. Just throw that pixel right out and give it no data. So it's a faster way to do this analysis. Let's give it an output name. I'm just going to call mine stream raster 2. And they should be identical because the underlying math that's going on is exactly the same. So they've just come in as different colors, but you can see that they are identical images. So once we've created this raster of all of the stream channels that are interesting to us, the next thing to do is to order them, to create something that ranks them based on how many other channels are flowing into them. And we're going to do this back in our hydrology tools. So I'm just in my toolbox, I'm in Spatial Analyst again. I'm going back into to hydrology, and what I'm going to choose is stream order here. So in stream order, it's going to ask me for my stream raster. This is either one. You should hopefully just have one. If you followed along with everything, you have 2. If they're identical, it shouldn't be a problem. It wants that, and it wants my flow direction to come in. Now, in the lecture part of this, I talked about the 2 different methods, Strahler and Shreve. Just leave it on Strahler. They're really kind of equivalent data. They're just different ways of ranking them. And I'm going to go ahead and spit it out as Michiana stream order. .tif. And go ahead and hit OK. So this will run for a moment, and it should come up with something that's ranked for us. And that's exactly what's happened here. So it's ranked them based on the number of other channels that are flowing into them. If for some reason yours comes up, if you're using an older version of ArcGIS, there was a glitch in the program where this might come up as nothing but once. So it would look almost identical to the stream raster here. If that happens, when you do it, don't specify the output raster. Let it go to that default one that it has there. It'll come out properly, and then you can just simply export a new copy of it or work with it from that temporary location. It was just a weird little problem with some of the earlier versions of the software. So once we have our ordered, ranked things here, the next easiest thing to do is to turn this into a vector file. So what we have here is lots and lots of areas that are not actually anything important, and bigger ones that sort of feed into each other and are very linear. So we want to convert these into a feature polyline shapefile. So we do that with stream to feature here. So choose stream to feature. Input your stream raster. In this case, it's the ordered one. Input your flow direction raster. You can leave it on simplify polylines, it's fine. And we're going to spit it out as Michiana drainage paths. You can put .shp if you want. Don't put .tif because this is a vector layer. It'll default to it as well if you leave it blank. Let's go ahead and hit OK. And now what we should end up with is a vectorized version of this that maintains the ranks that are in there. So it's not going to be immediately apparent until I turn off some of the other layers that are in here. I'm going to go into my layer properties for Michiana drainage paths, either by double-clicking or right-clicking and choosing properties. I'm going to go over to symbology. I'm going to choose quantities, graduated symbols, and go to grid code. So grid code here is whatever was coded into that raster that was there. It'll yell at you about the maximum sample size. That's fine. It just means there's lots and lots of little polyline segments in here. And since there's 6 different values possible, I'm just going to change my natural breaks to be 6. So it'll do this for me. In this case, I think it's probably good to change my template so that my water is blue. So I'm going to do that. So it'll change the color without changing anything else about them. Hit OK. So I accidentally zoomed in a little bit there. But what you quickly notice is that the very big channels, this is the St. Joseph River, so it's not a surprise. This is just a big channel sort of leading off of another part of the area. And some of the other ones flowing out to the edges are the larger ones. So a couple things you may notice on here. If you see spots like this right here where lots and lots of things are happening linearly and flowing almost exactly the same direction, that's usually an indication that there's a lake or something there, and the sink has filled, filling the sinks has filled it all to the same layer, so it can't really resolve that it flows together. Those are just little artifacts that show up. They don't mean anything, but your eye will start catching them and making you realize that that probably means there's something quite flat right there. So now that we've done this, we've created sort of how water is going to flow across the entire surface, where it's likely to collect, where it's likely to sort of build up. And the next step, or the next stage, is to look at the drainages of individual points. So there's a few different tools we're going to work on in here. I've just zoomed back all the way out. I'm going to go ahead and turn off my drainage paths for the moment, just because it takes a little while to render all of those lines. But I am going to turn on my filled DEM, just so I have an idea of the area I'm looking at. So the first thing I want to do is look at the flow length. So essentially the flow length is how far each pixel of the DEM it's going to flow before it leaves the edge, before it reaches the edge of the data that we have. So go ahead and choose flow length. You want to bring in your flow direction raster. I'm just going to minimize some things over here so that I can see everything in one. So flow direction. And I'm going to call it Michiana flow length. .tif, this is a raster that it's outputting. And what it's going to show me is for each pixel how far it has to travel before it leaves the edge. So this would be quite useful if you wanted to say have a correlate for how long something's going to stay in the area. If there's a spill in a particular spot, how long it's likely to stick around. And this becomes very apparent what's going on if you turn on the drainage paths as well. So you see that stuff over here has to flow all the way down here, all the way back into the main channel, and then all the way back off before it leaves. So these are why some of these are the very, very long ones, is they have to flow quite a long distance before they get out of the image itself. Whereas stuff over here just has to flow down a little bit, so it has a much lower value in there. So this is just a simple little analysis that you can run to get some idea of how long water is going to stick around. Obviously, if you had a bigger DEM, if you had a bigger extent for the DEM, it might be different. It might even be relatively different and absolutely different. So the size of your DEM initially does control quite a bit of what's happening here. So I'm going to turn drainage paths off again. And the other tool that I want to run in here is what's called basin. So we've talked a little bit about watersheds, so the area, the catchment of a particular point. What the basin tool does is it runs this for the entire area. So it's going to divide the entire area up into different basins based on sort of where they pour out of the edge of the image. So it's similar to the flow length, but it's going to be a little bit more of a categorical way of looking at it. So choose basin. All it wants is our flow direction. Make sure it's the flow direction filled. And I'm going to call it Michiana Basins. Again, I just chose another one there to then change the name. So it'll run for a moment. And it'll divide up the entire area into basins. Now the vast majority of them are going to be very, very small little ones around the edges. So there's 1,600 in here. Some of them are enormous, like these big black ones here or the ones down here. But the majority of them are little tiny things where there's one little section that only flows off the edge. So you could do some sort of classification of these based on their size. If we open the attribute table for that raster, you'll see how many pixels are in there for each one. So it would be fair to say that anything with a 1, probably less than a 10, is not really important. But some of the really big ones have many different pixels that are flowing, that are sort of classified as the same thing. So I'm just turning these off so I can see everything beneath it. And the basins, as I just said, the basins works off of doing it for the entire area. But what's often more interesting is to, say for Notre Dame campus, to find out how water is likely to flow across a particular intersection or across a particular site or through someone's yard. And that's where we bring in what we call pour points. So pour points are an area where we can classify the size that's flowing through that particular spot, the catchment of water that's flowing through there, the watershed of that particular point. So we're going to do that by first creating points to sort of measure this off of. So the first thing we have to do is create a new shapefile. This should be familiar if you've worked through the demonstration where we worked on vector data and creating new vector data. But if you haven't, you go over to the catalog tab. It should be on the right. If it's not visible, you can probably get to it through Windows Catalog as well. Find your folder and folder connections. Right-click on the folder that you want to build this into. So I'm going to right-click on Demo 12. I'm going to choose New Shapefile. And I'm going to call it Pour Points. I don't need to put the .shp on there, but you could if you wanted to. It is a point shape file. The coordinate system I want to go ahead and specify. It's going to be our usual one. If you followed along in a previous one, it might show up in your favorites up here. If not, it's projected UTM WGS 1984 Northern Hemisphere Zone 16 North. Now I do just want to specify one more time here that this is the UTM zone for Indiana and a good chunk of the Midwest. If you're working on data from elsewhere, you're going to need to know your own UTM zone and not necessarily use this individual one. Hit OK, and then OK. What we now have is a new shapefile to begin working with. So before we do anything else with it, let's go ahead and right-click on it. We're going to go to Edit and Start Editing. So now we're ready to begin building new points in here. If your Create New Feature tool did not immediately pop up the way mine didn't, it's right on the end here. Just choose that, Pour Points. Make sure it says Points. So you might be starting to run out of space on here, but we're just going to put them randomly kind of across here. One thing I want to be very clear that you're not doing, because it'll make a difference later on, is don't have the drainage paths on. If you have the drainage paths on, it's going to snap directly to them. Kind of defeats the purpose of doing the next thing we're going to do. So make sure that they're off. And then I want to try to just see what the catchment is, what the area flowing through some particular spots on here are. So I'm going to put about 10 points on here. Put one down here, put one over here, and then just a few others that aren't really in the middle of big areas. Try to catch whatever's flowing down from the top there. So I think that was around 10 or so. Before you stop editing, just so the computer knows the difference between these, go ahead and open up the attribute table for it. Right-click on it in the table of contents. And just this ID field over here, just go through and just change the numbers. I'm just going to do 1 through 10, or 1 through 11 rather. You're welcome to do different numbers in there if you want. Once you've done that, this just gives them individual IDs that you can use. Make sure you clear any selections that are going on. Go to Editor, stop editing, and say yes to saving your edits. So you've now created a new pour point shapefile. We're going to be able to see what the catchment is for each one of those points by using the watershed tool right here. So the first thing it wants is the flow direction, Michiana flow direction filled. The next thing it wants is the raster or feature point pour point data. That's what we just created. Ours are features right now, so to bring that over, it's going to ask you what the pour point ID field is. In this case, it's ID. And I'm going to give it an output as Michiana watersheds raw.tif. Now the raw, again, should give you an indication that we're going to do this a second time. So go ahead and hit save and OK. And it's going to calculate how much of an area is going to flow out through each one of these points. And it's going to give us a new image that probably doesn't look like particularly much. Largely because I'm not super good at clicking the one little pixel that watts of water is going to flow through. So it probably looks like very little happened. If we zoom in enough, we'll see that there's a tiny, tiny, tiny little watershed associated with point 2 there. And there should be with each and every one of them. In this case, I did a little bit better. I got maybe the area where 15 or 20 pixels is going to flow back out of. You may have done a little better. If you have enormous ones on there, you probably still had the drainage paths on and it snapped directly to them. But if you didn't, then you should have something that looks kind of generally like mine does here, where there's not a lot of area being caught by them. Now this isn't probably a very good measurement because the way that it works is water is going to flow through one pixel and one pixel only as it accumulates. Now realistically, if you're a little bit close to that pixel, if you're 5, 6 pixels on either side of it, you're probably going to have a lot of water flowing across you as well. So what we want to do to give a slightly better measurement is to move these pour points so that they're in kind of the maximum flow accumulation for an area. This will give us a much better indication of what the drainage through that spot is. So this tool that we're going to run on our original pour point shapefile there is snap pour point. So go ahead and double click on that. Bring over pour points. The ID field should be exactly the same. The input accumulation raster is what we want to work with. So that's going to be Michiana flow accumulation. And I'm going to go ahead and make the snap distance, this is a 30 meter resolution DEM. So I'm going to go ahead and say, as long as you're within 10 pixels of that spot, that's probably good. So this is going to be a little bit of a you want to decide what you want to do here. So this is 300 meters. That's a pretty big flow direction, our radius to have around our snap. So if you're using a smaller region, you may want to make it 100. You may even want to make it smaller than that. But don't leave it at 0 because it won't move anything at all. So I'm going to give it an output as snapped pour points .tif and hit save. And when I run this, I'm going to end up with something that's a little bit different. I'm going to end up with essentially a raster version of a point shapefile. That is in no way what that's supposed to look like. So this is, remember I talked a little bit before about an error that's in there. I'm going to go ahead and remove this because what this has done is incorrect. I'm going to rerun my snapped pour points tool. I'm going to bring over my point feature data. I'm going to bring over my flow accumulation. And what I want to do here is I'm just going to leave it as the default name here. I'm not going to change anything there. I'm going to put it at 300. What this does is it sends it to that temporary location. That temporary location is a little bit more forgiving about some of the glitches that happen. So just run it like this. Hit OK. If you really want to save those snapped pour points, you can by right-clicking over here. This is the new layer that just came up. Choosing Data, Export Data. We're going to specify the folder first. So I'm going to find my Demo 12 folder right here in the location. And then the name I'm going to give it is going to be what I said before, snapped pourpoint.tiff. So I encourage you to save this thing permanently, but it probably will give you that same thing where you have those little windows and that kind of really weird looking layer. So hit save. I'm overwriting one because I already created one that didn't work. So I'm gonna say yes. It's fine with me to overwrite that erroneous one, and to add it in, that's fine as well. So I'm going to remove that temporary one. Right-click, remove it. Now what this will look like, I'm going to turn off my watersheds over here, and if I zoom in on my points here, you see that I have a point right there, and then 1 pixel over here that's within that 10 pixel radius. This is where it's moved it to. This is the area within there with the highest flow accumulation. And it should be that way for every one of them. So if I go look over here, you can see it's moved it over there. So 300 was a pretty high difference. Realistically, you may want to do a little bit less. All right, so now what I want to do is rerun the watershed tool, and it'll give me a better idea of how good those were. So I'm going to rerun watershed. Again, it wants my flow direction. So that's going to be Michiana flow direction filled. It wants my raster or feature pour point data. Well, now I have raster pour point data, and it's snapped pour points. The value field is value. I'm going to call it Michiana watersheds snapped. Hit save, hit OK. And now when this runs, it's going to give me much bigger watersheds because it's moved it within that radius to a better point. And I should end up with something that's a little bit more representative of how water is going to flow across the entire surface and then how it's going to leave through those points. So that one that I did that's in the middle of the St. Joseph River there, it's actually catching everything that's upstream of it now. Oops, I zoomed in on that, I'm sorry. The same thing is true for some of these other ones where it's catching quite a bit of water that's flowing out from the sort of higher slopes over here. And the same over here. So these are more indicative of how water is actually going to flow across the surface. So that is most of the demonstration on using the hydrology tools. We've gone through almost all the ones that are in there, and this is how you would work through hydrology, getting several different layers that might be useful to use elsewhere in a model. So I encourage you to let me know if you have any questions, and please do follow along with the assignment. Thank you, and have a good day.